Ladies and gentlemen, welcome to this session of very fundamental ICT nature, namely 6G radio. My name is Pouttu, and I will be your moderator of this session. Since the times of Guglielmo Marconi, radio has developed to new heights, and now in the dawn of 6G research, we need to push the technology envelope of the radio to totally new territories. Next slide, please. If we choose to believe that in 6G wireless connectivity, you may click one more time. If we choose to believe that in 6G wireless connectivity, at least for the super efficient short range radio, 1 terabit per second data rate, less than 100 microsecond latency in the air interface, and 1 microsecond jitter in control is the design target of 6G, then we must with great probability assume that new waveforms shall be considered for conveying the bits in the air. And almost regardless of the chosen waveform, it means requirement of tens and even 100 gigahertz bandwidth of the data conveying signal. Now, this translates to a need for using spectrum way beyond 100 gigahertz center frequency. And now we face a very pragmatic challenge in terms of devices, circuits, and materials. We do not have at the moment the semiconductor materials and processes to fabricate the circuits and designs at good power efficiency. Furthermore, the new materials and extremely high frequencies may entail new physical phenomena that raise the need for new circuit design principles. Also, AI implemented in the radio as distributed computing intelligence needs totally new thinking as the current AI solutions are developed and targeted to big data opposed to the small data algorithms needed in local radio environment. And in terms of new applications, how do we deploy radios inside, for example, car windows, in wearables, inside the chip themselves to replace wired connection between different chips inside the devices? Next slide, please. Some of these aspects, you may click one more time. Some of these aspects and also many more in terms of research visions are discussed in 12 white papers provided by the 6G flagship in collaboration with 250 global experts in different fields, covering topics such as UN SDGs, 6G business, technology enablers, for example, for security, networking, communication, sensing, locationing, and vertical use cases. Next slide, please. As a teaser for the audience, a new white paper is recently out, namely RF enabling 6G, opportunities and challenges from technology to spectrum. I will not go into any deep discussion on this white paper, but you can see the web addresses where you can attain a copy of this particular white paper. But that's enough on warming up. If we go to next slide, please. We have 4 excellent speakers today, who many of you most likely know. We have Gerhard Fettweis, who is Vodafone Chair of Mobile Communication from TU Dresden. Our second speaker is Harish Viswanathan, Head of Radio System Research Group in Nokia Bell Labs. Next slide, please. The third speaker is Izzat Darwazeh, who is actually a professor in University College of London. And our fourth speaker today is Yima, Reader in Cognitive Communications, University of Surrey. And without further ado, we go to next presentation, which is provided by Gerhard Fettweis. And he got his PhD from University of Aachen in 1990, after which he went for 1 year in IBM research in San Jose. And he moved to TCA Inc. and in Berkeley, and since 1994, he has served as the Vodafone Chair Professor in TU Dresden. Gerhard Fettweis is IEEE Fellow, member of the German Academy Acadec, and his most recent award is the Stuart Meyer Memorial Award from IEEE VTS. In Dresden, he has spun out 11 startups and set up funded projects in volume of close to €500 million. He has helped organizing countless IEEE conferences. Unfortunately, Gerhard cannot be live today here. However, he has provided us a inspirational talk on 6G as he just in the last minute was detained to some other business. But here you can see his video.
Ladies and gentlemen, I want to welcome you to my talk on 6G's chance, in particular trustworthy IoT and new functionalities. If we look back, where do we come from? Where are we today? 1450, physical print was invented, and this started 300 years of Renaissance. 1989, electronic print was invented, the HTTP protocol, and this started something like a new Renaissance. Obviously, there are big differences. So the first Renaissance made it possible for people to read and write and not to have this only as a monopoly of the monks. The second Renaissance made it possible for everybody on the world to be connected and to print their ideas, post their ideas to the whole planet Earth, not bound by the speed of the horse in transportation, but the speed of light. And the copying speed of transmitting this information all over the place is the speed of electronics and not of a physical printing machine. So this is a huge additional step in mass communications. Just like people say Renaissance 1.0 was the invention of mass communication, the second Renaissance that we're living right now is a new big step. And it's about communications. So now we have to ask ourselves, what can we learn from the previous Renaissance, from Gutenberg and Luther, to take us forward to learn about our today's situation and understand what's happening? Obviously, today, if we look at it, we talk about the Turing galaxy. Previously, we had the Gutenberg galaxy. Previously, the previous Renaissance made it possible for Luther to come up with his ideas. Today, we have Twitter to generate ideas all over the place. Previously, we had the Renaissance. Now we have sort of the second Renaissance. And this is something we have to come to understand, and we have to understand which role do we play with our industry, which role does 5G play, which role does 6G play, and where is the role also for semiconductors in this whole thing. We have to obviously learn from history, because history doesn't repeat itself, but it does come in rhymes. Now, what is it about? It's all about communication. It's all about information and misinformation, and it's hence about trustworthiness. Only if we understand the topic of trustworthiness can we build a stable society, can we build everything to function in a way that we would like it to be. To make sure that we have this happen in an internet of today, we have to start with anchors of trust in this kind of a network that then spread out over the whole network. Now let's look at how this plays in the context of 6G, and where does a sense of urgency come to play with understanding the topic of trustworthiness in the context of 6G. 5G is what we have today. We're at the verge of really understanding rolling out 5G in a big scale and understanding what this is. The new functionality in 5G is teleoperation of objects. Again, not for consumer markets, but for business opportunities, like in the construction industry, in agriculture. Down below, the three photos you see here are pictures from our own test bed. The top is from an animation of our own construction test bed that we have. So you see these campus networks being operated with the teleoperation of objects for business customers mainly today. But what we would like to anticipate is go to a football stadium or soccer stadium and see a game there. You would have your AR goggles on and you would say, I want to watch the movie, not only the movie, but I would love to watch the game out of the viewpoint or the perspective of one of my favorite maybe players on the field. So this should be projected into my goggles so that I see the red player that is in front of the white guy. Or I want to even zoom around as the ball and get basically the ball's perspective into my goggles. So this level of interactivity is something we still dream about. This is something I talked about 10 years ago. This is still not there in terms of 5G. 5G is for business, but we dream about these kind of cool consumer application. What are other consumer applications we dream of besides VR and AR, where all the different requirements come from? Obviously, we would like to look at this in terms of teleoperation of objects for consumers. We know already interactive games like our ball machine and a tennis court, or we have this little robot here that you see that we're playing around with already in our test beds. Or you see here a person that is paralyzed that with the help of exoskeleton can start walking again. This will be enabled with 6G. We will have consumer products that kids can play with, grown-ups have as helpers in their home, or when we become elderly or we're impaired, our life becomes much nicer because we can move around more freely and have way more mobility. So the idea is, if you look at this, these are not what I showed you as the topics on 5G. These are consumer mobile robotics examples. So again, what we see is 1G, 2G was voice, 3G, 4G was data, 5G, 6G is objects, telephony, mobile internet, tactile internet, 1G business customers, 2G consumer, 3G business, 4G consumer, 5G business, 6G will be the consumer market. And why is that important to know? We would love to buy at least one of these consumer products every 24 months, just like we buy a new cell phone every 24 months. And if you look at that and just look at the market opportunity, that means if every European was to buy a new such mobile helper every 24 months, we could easily fill a nanometer fab in the best node possible, because the amount of semiconductors needed for that is so humongous. So this is our chance. We have to understand that we have to enable this mobile consumer products, these personal mobile robotics, because they will then also enable the semiconductor industry to provide the full food chain into this kind of system design and really thrive on these new markets happening. So if we think of that and think of this opportunity that 6G will bring to us, the question is, can we just do that with 5G? No, we cannot. We're actually in desperate need of additional functionality. Let's have a look at it. And we are in need of trustworthiness, because obviously, if we have these objects running around, the first thing we want to make sure is we can trust these devices. They don't harm us, they don't destroy us, they don't hurt anybody. Nothing is going to be happening. We fully can trust these. If today something happens to your phone, bits and bytes are lost. If tomorrow something happens to your mobile robot, it could be more than bits and bytes being lost. So that's why it's important that we lay the foundation for a digitized democracy to put in trustworthiness in the internet. And for 6G, we have to start with the IoT nodes. We have to have trustworthy IoT platforms. So how do we do this at the node side so that we can for sure enable these great new applications that will be happening and generate these opportunities for the semiconductor industry and of course for all the consumer industries that we are very strong at in Europe these days. For this, we have to look at this in terms of the hardware software part. This has to be composable, trustworthy, verifiable, such that we know this is what it is. We at the same time have to make sure that, for example, we do physical layer security to make sure that we have our trusted wireless connectivity and that is not impaired. And we have to have new functionalities going beyond that. We have to do sensing, because these mobile robots need massive amount of sensing, not to bump into something and not to accidentally make the wrong move. For that reason, we have generated the new Backhausen Institute 2 years ago. Since 2.5 years, we're in action. And basically, we're addressing these different topics. It's the trustworthiness of things from a software and hardware point of view. It's the trustworthiness of the communication, the connectivity, such that we don't lose the trust on that side. It is the trustworthiness of the context. We know what's going around, and we're not going to harm anything, but we're going to do exactly what is intended. And there has to be the fourth part. We have to reach out to society and make sure that we also build trust for these new things by reaching out to society. I think these are really truly important topics that we have to address. And that's why we started this new Backhausen Institute. Now let's talk about these first bluish three topics, the key concepts, and pick two of them. Trustworthiness of the things as one. If we look at a thing is always defined by software and by hardware. Today, software is written by people writing software, hardware is designed by people designing hardware. And we say we somehow tape security on top. That is an issue. What we really have to make, software and hardware are interlaced and truly build a secure system. And it's not like Teflon sliding on top. In our current way of doing things, we don't have to be surprised to see a meltdown and a specter happening. In our future way, these things, the software system, the operating system, and the hardware are interlocked and truly give us the trustworthiness such that we feel trusted and secure. This is how we have to design systems. This is the first example of what we've achieved so far. Here we have our own trustworthy multi-processor system on chip platform with our own microkernel decomposable operating system, where we really make sure that the hardware and the operating system are closely interlinked so that the trusted anchors that the operating system need are in the hardware and vice versa. And this is just the first step. There are certainly many more challenges to get this up and running into a full-fledged kind of scenario to address the 6G challenge of the future. But it's a first nice little step. Now, how about not only touching trustworthiness, but I mentioned there will also be new functionality that is needed. What does that mean? Obviously, we are humans, we have senses. And we have also certain senses in nature that humans do not have. In 5G, with the tactile internet, we talked about remote control and senses in this kind of a context. That's great. And we have quite a bit addressed already with this kind of view. But what we're missing is like taste, smell, and echolocation. So we are missing the ambient cognition. We don't really get the ambience that we have around us in a sensing way. Why do we need that? Well, if we're talking about really remote controlling objects, and this is a car on the road, and there are leaves in the way, or tumbleweed, or whatever, your radar system says, full stop. That's a bad idea. As a human, you see, you can slowly move forward because we can differentiate easily between objects that are like this, a dead object, or a possible live object. So we need not only radar, we need also spectroscopy and true identification of objects. And this is something you cannot only do with cameras. The second part is in our virtual world, we want gesture detection. We don't want to have funky gloves that we wear to do AR, VR interaction, but we want to have our hands and gesture detection. So we need way more for the future than just communication. We need these new sensing capabilities. And that's why the question is, can't we possibly do this in the same spectrum, in the same system? Today we have two different systems, one for radar and one for communication. Two spectra, one for automotive radar, for example, and one for cellular communication. We get 5 gigahertz of radar reserved for free for 1% of the population that can afford having a car with radar. 99% of the population has to spend dearly every month for the spectrum that has been bought and licensed by the operators, and every month we pay with our monthly bill to the operator. That makes no sense. We need to somehow come to a solution because we need more radar spectrum to be able to solve the problems of the future for these new applications. Because the radar is uncoordinated. There is no medium access control. It is everybody chirps around just like they want. We need to be able to build a coordinated radar system. And the way to coordinate that is to embed this in a communication of the future. That doesn't mean we don't keep the radar systems as they are. That we do, and keep the communication systems as they are, possibly also. But the new spectra and the new communication system has to be able to do both. If we do that, we can share one spectrum and dynamically use in a situation the spectrum, the channel for radar or for communication, and then match it according to the needs. And that is where this whole thing makes more sense. And this is where we then also add the ambient intelligence, the ambient sensing on top of just the communication part. That means we generate trustworthiness of the context. We know what we're doing, and we're not going to harm, we're not going to bump into other objects, and we will be able to actually do this. For this, we have the group led by Padmanabha Sen at the Barkhausen Institute, just to give an idea. We really try to understand this in this context of secure, context-aware radar embedded in the physical world for giving us the trustworthiness of the future, such that we can trust these devices that they don't misbehave but obey exactly according to the intended way. A possible way of doing that, of course, this is just one possible solution that we demoed already 2 years ago, is if we take the chirps of radar and use them also to modulate data. And we have nicely shown that this is possible. You can then also build these kind of radar systems embedded in communication systems or vice versa, depending upon how you look at it, and then have this kind of approach. What is the good news? The true good news, the amazing news. If we talk about semiconductors and sensing in general, Europe is really strong. Europe is also strong in robotics and automation. And Europe is strong in communications. And Europe is strong in consumer products. Not so much electronic products, but if we're talking about personal mobile robots, these are consumer products in sports, in gardening, in whatever, or white goods, all these areas where Europe is strong. And so what we really need for this 6G opportunity to happen of personal mobile robotics is for these to come together. And this is a pole position Europe has. Europe is strong in all three, and hardly any other area on planet Earth has this kind of combined strength to be able to address these great new markets that will be happening. So in conclusions, what have we learned? 6G is amazing. It will take personal mobile robotics really into the consumer world. Today, it is business mobile robotics with 5G. 6G will be personal mobile robotics with applications for kids to game, for grown-ups to have an easier life, robots taking care of our life at home, all the way to when we become older and need additional help. That only works if we have a level of trustworthiness that goes way beyond what we have today. Obviously, we also need to address integrity of the system and energy challenge. I didn't touch those parts. But we also need to be able to then build a trustworthiness of our ambience around us. For this, we need additional functionalities that go beyond what we have in today's cellular system. It's not only about transporting bits and bytes, it's also about sensing our ambient environment. And for this, we really need to generate something new. So 6G will be something really, truly new, also from the whole air interface, the radio access networks. The opportunities are plentiful, be it in gaming, be it in helpers, be it in assistance. The market will be huge. we will want to buy one of these things every 2 years to make our life more fun, to have an easier life at home or in the yard or wherever we are, or be more mobile in future. So our responsibility now and here as an industry is to truly make sure that we understand these are the opportunities coming ahead. For that, we have to lay the foundations to build true trustworthiness into our IoT nodes. We have to come up with these new ways of doing that to have a trustworthy digitization to build our societies of the future. The good news is this also comes in accord with new opportunities for Europe, because Europe is strong in that. We see Europe has a pole position to grab these 6G opportunities, and we really should make sure that we take care of these and grab them by the horn and make this happen. So it is the opportunity of our lifetime. Starting with the 2030s, Europe can be really a main contributor to making the world a better place. And with 6G opening up and the 6G window starting, this will happen if we embrace these ideas. So thank you for listening, and hope that you will have a lively discussion.
That was a very great presentation by an inspirational presentation by Gerhard. But as I mentioned in the beginning, Gerhard is unfortunately detained in something else, and therefore we cannot take any questions. And thus we go for next presentation, which is given by Harish Viswanathan. He is the head of Radio System Research Group. He leads an international team of researchers investigating various aspects of wireless communication systems, in particular in 5G and now in 6G. Harish joined Bell Labs in 1997 and has worked on multiple antenna technology for cellular wireless and mobile network architectures, as well as machine-to-machine. He is a graduate of Cornell University in Ithaca, and he holds more than 50 patents, and is a fellow of IEEE and Bell Labs fellow as well. So, Harish, if you please.
Thank you, Ari. Thanks for the invitation to talk. So yes, the goal of this presentation is to describe the radio innovations that will be needed in the 6G timeframe. Before that, let me start by asking, what do we want from 6G to motivate what kind of new innovations we need in the radio? I will quickly go through this. So we are also focusing on the human, and our vision is to say we are going to augment the human in 3 dimensions. The first one is about augmenting the human experience. To me, this really is captured by saying that we are going to create and consume digital worlds, and our applications of the future will be built on entire digital worlds like they are built today on multimedia. And there are many use cases, and I'm not going to touch on those. What does this mean for the 6G radio? It means that we need ultra high capacity, low latency, both outdoor and indoor networks. The second augmentation of the human is augmenting the human intelligence. Today, we search for information from our networks through the internet. In 2030s, I believe our machines will be infused with artificial intelligence, and we will be relying on and learning from machines and with machines. And this essentially translates into increased awareness of the context and the environment through sensing. And so what we want from our radio is pervasive sensing and the capability to embed machine learning and artificial intelligence throughout the network as well as in the environment. Then we have augmenting human control. As we heard, we are going to be in an era of robotics, personal mobile robots in both consumer and the industry space. And we will have more sophisticated needs for communication, both between humans and robots and between robots. And this means we need highly flexible and agile networks, in the sense that the networks would have to be deployed in different scenarios: verticals, special area networks, homes, etc. Finally, we need sustainability, affordability, and resilience from the network. And this I translate into multidimensional efficiency at the radio level. So we are not just focusing on spectral efficiency, but we are focusing on energy efficiency. And as always, we focus on cost and we focus on resiliency, ability for the network to continue to function in the event of some disaster. Robustness is what we mean by that. So if these are the requirements, then how do we get them, or what are the technologies that are needed to achieve them? When it comes to capacity, we now know that massive MIMO is going to provide us the biggest benefit. And so we have to improve massive MIMO at the radio level for the next generation. There are a number of issues that I'll talk about for massive MIMO enhancement. Obviously, we're going to need more spectrum. Just increasing spectral efficiency alone is not enough. So we have to have radios that function in new bands, adjacent to existing bands, as well as in higher bands. We need the joint communications and sensing to enable the pervasive sensing of the environment. And the radio has to be integrated into the network, into a simplified and automated network. So the network automation has to extend down to the radio so that one can easily deploy and automate the connectivity as well, not just the services. Finally, to have these agile networks, of course, we are going to have a need for enhanced privacy, trust, and security technologies. And then when it comes to efficiency, energy efficiency is critical, as well as sub-networks are also an important piece. This is realizing that the device itself might become disaggregated and become a network. And so we need to design not just for a single devices, but a network of devices that are tightly coupled to each other. But underneath all this is the native AI ML framework for both the air interface and the network. And this is the context in which our radio will operate in the future. So I'll touch on some of these topics going forward. The first one is starting from the AI ML air interface. Why do we believe that there is potential here, and what does this really mean? So traditionally, you can see the transmitter and the receiver blocks. These are the signal processing blocks. You're communicating from A to B. It goes through a channel. You have on the transmit side coding, modulation, and things like that. And on the other side, we have the decoding, etc. The first step in the evolution here is to replace individual blocks through machine learning, and in particular through deep learning. And we would do this because it reduces complexity or enhances performance, really. And this is happening already in the 5G timeframe. But the real advantage of machine learning comes when we go beyond these individual blocks replaced by machine learning to jointly optimize across multiple of these functional blocks. So now we are talking about true end-to-end machine learning for various functional blocks. And this has several advantages, performance being one of them, but it also means that it can make the research and development simpler, faster to innovate, faster to modify our air interfaces, make it more adaptable to future modifications. It can be multiple links or multiple connectivity approaches for different kinds of environments. We don't need to have a single sort of configurable interface for all scenarios that we are going to operate in, but it can be more learned and adapted to specific environments. So these are some of the reasons why I believe that we will see at some point eventually networks or radios incorporating these sort of machine learning techniques. So here's one example where the constellation has been designed using machine learning. And you can see that this is not one of the traditional constellations, but the machine learning has learned to do constellation shaping because it provides some signal to noise ratio benefits. The next challenge is the massive MIMO challenge. So today we are building 64 TRX radios, but that's not where we think the limit is. As we go to slightly higher bands, 6G bands might be in the 7 to 15 gigahertz, So you're doubling the frequency of the mid-band, and that means we can accommodate many more antennas. How do we make use of that? We need low cost and low power radios that can scale to much larger arrays, 4 times the array sizes, 4 times the number of transmit receive chains. We need more flexibility in terms of what bands radios can operate in, what can the bandwidth be, and we have to optimize for the power consumption when we try to combine multiple bands into single radios. And we can look at new techniques like optimizing the waveform for massive MIMO to reduce the peak to average power ratios, even in the lower bands, because then it reduces the cost of the radio. Advanced signal processing is a given when you're talking about massive MIMO. So to increase the spatial multiplexing and really benefit from the spectral efficiency, we need sophisticated signal processing and now machine learning based signal processing. And then in some contexts, we can even think of arrays that blend into the infrastructure, I mean the physical infrastructure that's deployed. So this means that you need to have a modular approach where you can build a large array using small elements that can sort of make the array conformal and invisible. These are some of the new challenging problems that I believe we have to solve in massive MIMO. Moving on to sub-terahertz, there are a number of issues here. So these are the higher bands that we believe that 6G might need to really provide the very high data rates where it's actually needed, mostly indoors, small cells, or for backhaul. And here we are talking about problems such as waveform design, how to produce devices that can do higher output power. So it's very hard to do high power power amplifiers in these bands. We need RFICs that can build phased arrays so that we can actually do beamforming. And then finally, we need to learn a lot about the channels. So in terms of the ongoing work, our analysis on the analog to digital conversion power consumption is shown here. And we compared the power consumption across different resolution of the A to D. And what you see here is the power consumption for up to 8 bits is not a huge fraction of the overall power consumption. So the point here is that even in these high bands, we can afford to have reasonably high resolution, but not digital. Clearly, if you go digital, the power consumption grows very high. And this is also the reason why in millimeter wave, we already do not do full digital, we do hybrid beamforming. And of course, here I'm just showing the percentages, but the digital, full digital chains have 10x more power than the analog. So that's the reason why we probably will stick to analog or hybrid. But my point here is that we can actually build radios with higher resolution even in these bands, and we don't have to rely on 1-bit ADCs. The figure on the bottom is to make the point that some new waveforms may be needed. We compared OFDM, the DFT spread OFDM, and the single carrier frequency domain equalized waveforms. What you see here is spectral efficiency versus the EB over N0 in the presence of phase noise and with some phase noise compensation. If you want simple receivers, because imagine that we are now operating the signal processing at hundreds of gigabits per second. And so your signal processing has to be really simple. And so you cannot envision very complex phase noise compensation or ICI cancellation. And with that, it appears that for these higher constellations, the single carrier FDE performs the best in terms of the spectral efficiency versus EB over NZ. So we will do more research, but we are leaning towards these kinds of waveforms for these very high bands. Next is the joint communications and sensing, and clearly there's a lot of motivation for creating a network that can not just communicate, but also sense the environment. And this environmental sensing leads to new use cases, especially for network operators who will own the data if it's the base station that's doing the sensing. But in addition, it's also for optimizing the network itself, to build a digital twin of the network, for example, one can use the sensing that the network actually performs. The motivation is there, but is the technology ready for it? And these are the drivers we believe is pushing us in that direction. So as we go to 6G, we are going to go to more dense networks, not just the macro sites that we have today. And we are going to higher bandwidths, which means that the time resolution of sensing is going to be significantly better. We have already embedded sophisticated machine learning and signal processing in our radios and digital processing, which can be reused for sensing. And machine learning is very important here because modeling of objects that have to be detected, many classification tasks, these things naturally can benefit from the machine learning type processing. Because if you think about it, it's like a camera is a sensor and the computer vision is about seeing what the camera sees. And AI is extensively used there. And now we're basically saying that instead of what the camera sees, the radio is going to see its environment in a different frequency. But again, it's the same problem of taking the radio signals and identifying objects and seeing what the radio sees in human terms. So AI is going to be very beneficial there. And then finally, the massive MIMO arrays and the beamforming that we introduce in our systems give us sufficient spatial resolution to do interesting applications in sensing. So these are the drivers which we believe is pushing us in that direction, and it's going to be a very exciting innovation for radio in 6G. So in terms of early work, you can see that the kind of things you would expect in the future. So today we have data slots, data frames in the data slots in the frame for uplink and downlink. And going forward, we may see some radar slots in between these data slots. That's multiplexing of potentially a new radar waveform in combination with other data. And then there's going to be a lot of optimization on how frequently these radar slots have to be built into it. And of course, this doesn't prevent us from using the data transmissions themselves to do the sensing by capturing the reflections. But in addition, we may need extra radar-only slots. And likewise, we have the beam sweeping already today, and that is designed in 5G in a narrow portion of the spectrum, in the central part of the band of the carrier. And going forward, we may see additional beam sweeping introduced for radar, because these may not be sufficient or may not appear at the right time when you want to do the sensing. So these are some of the new ideas, and you can see the kind of challenges we will be addressing here are again around waveforms which are optimized for both sensing and communications. How do we do resource allocation so that we can still maintain low latency for communications? You do not want the radar to interfere with the latency and throughput that we achieve, and that is the whole point of sharing the spectrum, that you can achieve higher efficiencies for both by doing intelligent resource allocation. We talked about the beam sweeping. And the other advantage of communication-based system doing the sensing is we can not just rely on the delayed Doppler that the radar usually relies on, but we can actually extract much more information because we have pilot signals. We can extract the channel state information and process that to do more advanced sensing. Finally, of course, high precision localization is going to be very much part of this whole network as a sensor theme. So in conclusion, we have a lot of potential in innovations that are waiting to happen in the 6G radio space. And we should all be looking forward to it. Thank you very much.
Thank you. Thank you, Harish. There are a few questions. Maybe I'll just pick one of them. One question is that can this modular RF arrays, for instance, in conformal settings, can it mean less radiation in terms of space?
The amount of radiation depends on how much output power we put out from these radios. I think just because they are conformal doesn't necessarily reduce the output power. At least that's what I'm thinking right now, because what we are aiming for is a certain range and spectral efficiency. And so we will always be sure to meet the regulatory limits. But I'm not sure just changing the shape of the array is going to have a very big impact on the output power and hence the radiation. In fact, I mean, yes, some of if you have an irregular shape, then we'll actually need more signal processing to compensate for the array orientation and the shape and things like that. But in terms of output power, it's really what we decide to incorporate. Indeed, yeah, if you're really looking for very conformal transparent type arrays, then we are forced to do low output power because we need them to be small radios. Yeah, so then maybe that's the angle of the question here. So if you really are aiming for perfectly conforming, blending with the infrastructure in very weird shapes, then it's hard to do a radio that's high output power. So it will be lower output power per element, but the EIRP might still be comparable to what we have, because we need to have the coverage that we are aiming for.
Excellent. Thank you, Harish. We'll go forward because the time is limited.
Okay.
Thank you very much. Our next speaker is Izzat Darwazeh, who is a graduate of University of Jordan and later on did his doctorate in University of Manchester. He currently holds the University of London Chair of Communication Engineering and leads a 70-strong communication and information system group in the University College London. He has authored and co-authored more than 250 book chapters and papers, and written some books on high-speed and high-frequency circuits. Izzat is a chartered engineer and a fellow of the IET and a fellow of the Institute of Telecommunication Professionals. Izzat, are you ready to go? If so, please give your presentation. Thank you.
Ari, thank you very much, and thank you for inviting me to speak to this forum, and particular thank you to Harish, who will make my job a bit easier, as he touched on lots of points that would have served as a very good introduction to what I want to talk about. Having said that, he is a difficult act to follow, but I will try and do my best. Let me start by trying to share my screen. I hope that this works.
Yes, it works.
Excellent. Okay. Bear with me. Okay, is this sharing okay, Ari?
Yes, it is. Go ahead.
You. Excellent. Okay, so Harish, in the end of his talk, mentioned about, or towards the end of his talk, mentioned about new radio. What type of radio is going to be used for, could be used for 6G. And by radio, he discussed specifically modulation. He said modulation, how do we carry the signals, the information signals? And what I want to see, what I want to argue is there a need for new radio for 6G? Why does radio and modulation change from one generation to the other? Well, it's simple. For all our generations, for all wireless communication systems, cellular or not, but for the cellular specifically, we want to send lots of information with good quality in the smallest possible bandwidth, with the lowest possible energy, using the simplest equipment. All of these are contradicting requirements. Think of the first generation. The use dictates these requirements. What use? What are the utility that is required from a specific generation? Whether it is the analog of the first generation or the very high rate and multi-services of the 5G. The use dictates the type of signal that we need. And indeed, the first G, the second generation, mainly exemplified by GSM, third generation MIL exemplified by UMTS, LTE as a fourth generation, and the 5G, they all have a different radio. LG and 5G have slightly different radio, but the rest are very different from them. The data rates, we started with kilobits per second when I was an undergraduate. We are into the gigabits per second now, and we're moving into, as mentioned earlier, the tens and beyond gigabits per second to be delivered. The bandwidth, we started with few kilohertz of bandwidth, moved on to 200 kilohertz in GSM. Now we are going to look at aggregated bandwidth of tens of megahertz and beyond. Indeed, for 6G, we are looking at frequencies of transmission that could be in the high millimeter wave, high end of the millimeter wave, or what could be called the terahertz, with all the bandwidth that it can offer. We are always faced with the problems of the channel. The wireless channel is a terrible channel. Its physics is limited. The signal takes multipath, so there's delay spread. The environment changes around you. People move, you move, the environment moves. And so the channel physics are always problematic. And as we move from one generation to the other, we need more, we'll have more users of these channels, so we'll have more noise, more interference, more complex. And then we need equipment that will have to cope with this high bit rate, excellent quality signal, etc., with limited energy and complexity. It is, in my view, these requirements that made people look for different radio. And what I mean by radio here, I mean specifically signals with modulation and signal modulation and signal coding and signal structure. First G used FM, the second generation used GMSK, which is effectively a type of frequency shift keying or phase shift keying. UMTS used QAM type of modulation carried on CDMA signals, spread spectrum signals. LTE and 5G use, again, QAM modulation carried on orthogonal frequency division multiplexing, OFDM. With its varieties, you know, the single carrier FDMA is a type of OFDM, if you like, but you know, that's what we have. And the reason why we move towards OFDM is because it can cope with this bad channel, and it is a very good system for using for the high bit rate. So it satisfies many of these qualities. So is there a point of looking for other systems? Just a bit of history, by the way, and very quick. The concept of OFDM goes back to 1957, 1958. It was developed as a system for transmission of signals between computer rooms. And effectively what it does, it sends signals in parallel. And you all would, I think most people in the audience would know this, so I'm stating the obvious. Send signal in parallel. When you send signals in parallel, when you're faced with a bad channel, if one signal suffers, the other one will not suffer. These signals that are sent in parallel are effectively orthogonal. This is the picture for those who have not seen this stuff before. That's where the first OFDM systems were used in computer rooms. And the signals are sent in parallel, and if they're orthogonal, it means that they don't get mixed up. In other words, I don't know if you can see my mouse. If I look at the spectrum of an OFDM signal, the signal is divided across different carriers, and when one of them peaks, all the others are zeros, and therefore there is no interference in the frequency domain. There's no what we could call interchannel or subchannel interference. That is the meaning of orthogonality. I think everyone in this audience would know this. The system OFDM has been used in many, many applications. Other than LTE, almost most of the wireless systems that has been developed from the late 90s onwards have used OFDM or one of its variants. Jumping a little bit back in history, people may remember or know, people my generation, I think, and many of the people speaking today would know about GMSK, and probably many of the young people have forgotten that this was a thing that was used for GSM. And this is also a type of an orthogonal system, but where the signal spacing between two subcarriers, if you like, is half of that of OFDM. So where in OFDM, the spacing between two subcarriers is equal to the signaling rate, in GMSK, the type that is used in GSM, the distance between two subcarriers is half of the signaling rate, yet they are orthogonal. Many years ago, we looked at using something like MSK with multi-carriers, and we called it fast OFDM. I worked on this in 2002, and then this ended up as a system not used much in wireless, but used very heavily now in many optical systems. And then we looked at something in between. Can I have a system whereby the spacing between two subcarriers is not a multiple or submultiple of the signaling rate? In other words, I want to break this law of orthogonality to get the subcarriers closer together. We call this system spectrally efficient FDM, and I'm going to tell you a little bit more about this system as we go along, and argue for it that this can be a good system for what could become the 6G type of structures. If you bring the subcarriers closer together in OFDM, effectively you lose these zeros that happen whenever one peaks, all the others are zero. You lose this facility. This will create signals with high interference, this messy bit here or here, this high interference, and this will make the signals non-orthogonal. These are the signals that I'm talking about. I call spectral efficient FDM. So if I get here X number of carriers, get them closer together, I save bandwidth at the expense of this messy situation here. Or if I keep the signals all at the same spacing, but I transmit more data per subcarrier, I increase bitrate within the same bandwidth, but I will have interference. It is these systems that I have an interest in telling you about now as possible candidates for future systems and show that they can satisfy the requirements of what will become a 6G. We are not the only people who talked about this. This is now very well talked about subject. A group, an excellent group at the University of Lund in Sweden, not far from where Ari is now, worked on similar system, which is called multi-stream faster than Nyquist. And again, very similar signaling at a faster rate using non-orthogonal subcarriers. The question is, can we get rid of these high levels of interference? The other question is, by the way, which is of interest to people who look at any signal design for future systems, is can the amplifiers of the transmitters cope with them? In other words, one of the main problems of OFDM is that they have what's known as high peak to average power ratio, which will make problematic conditions on the amplifiers. And this PAPR, the question is, if we have non-orthogonal signal, does it have high PAPR? They do not. These signals will have even better PAPR than OFDM. Okay, so these signals, they seem to be suitable to us initially. When we started to work on this, we looked back in history and we found actually, like OFDM was invented in 1966, in 1975 at Bell Labs, Mazo looked at something similar, but with a single carrier, not multi-carrier, and he called it faster than Nyquist signaling. Very interesting paper if anyone is interested in looking at signal theory and design. So 1975, the work started. We picked up again, slightly different version of it in 2003. We want, as Harish said, you want to have simple way of detecting and of generating signals, when normally the best detection and generation of OFDM signals using FFT. We can do the same here, slightly more complex FFT, but we can generate these signals and detect them using FFTs. We have experimented with this. We built our own FPGA boards a few years ago, and we can generate these signals and detect them using FFTs and using standard FPGAs. And we also can be designed as in integrated circuits using standard cells. The main aim is to be able to reduce the bandwidth from an OFDM bandwidth, which appears here in red, to lower and lower bandwidth of this SAFDM and to detect it. The bandwidth saving we call alpha. So if alpha is 1/2, it means that we are only using half the required bandwidth for the same data rate. And if alpha is 2/3, it means that we are using only 2/3 of the bandwidth. The main problem is the interference. which is a problem. It is a function of two things. It is a function of how much we compress the signal, which makes sense, and it is also a function of the number of subcarriers. When we look at 4G, 5G, and later on 6G, we could be talking about thousands of subcarriers being transmitted in the signal. And this will increase the interference. And our aim was, over the past 15 years, we've been working on this, is how to be able to detect these signals with little interference. I'm not going to have time to look at the concepts of reducing this amount of interference so we can get good signals. I'm just going to show you some results. Okay. We have tested these signals over the years over different channels, from very simple additive wide Gaussian noise channels to more complex fading channels, frequency selective channels, channels with different type of fade profiles, etc. And let me just show you some results, if I may. If you look on this bit error rate curves on the left, the blue curve here, the lowest curve, is the OFDM. So the OFDM is the thing that you cannot better unless you use coding. If I aim to save up to 45% of bandwidth, more or less doubling the bit rate within the same bandwidth, I get this purple curve here. So this is the best case that I'm showing. Or this brown curve, which is in a slightly more complex type of arrangement. So the brown compared to the blue are using non-orthogonal format, but saving 45% of bandwidth, or doubling the bit rate, more or less doubling the bit rate within the same bandwidth. And what I see is that within a fading channel, I would lose something like 2 dB of bandwidth. Yeah, I'm sorry, 2 dB of error penalty to achieve the same bit rate. Well, what does this tell me? It tells me that if I'm willing to sacrifice a bit of signal power, a bit of bit rate, I can save bandwidth. We have experimented with this in different systems. We've experimented either using the VR5, which is a channel emulator. We've experimented with this using MIMO, not massive MIMO, but up to 16 channel MIMO systems. We have experimented with this, sending nice pictures. We have experimented with this using LTE type of signals, LTE framework. And actually, our plan was to use 5G signals, but then the pandemic happened and our labs were closed. And we'll be looking at 5G type of signals. So fitting these particular spectral efficient signals within a 5G signal frame to see how these things work. And in all cases, we can see that we can lose power, but gain bandwidth. And we can gain bandwidth easily. We can gain bandwidth up to, save bandwidth, gain spectral efficiency up to 40 or 50%, 40% without losing much power, tolerable power loss. This will make these signals quite attractive, because even though that 6G is promising us a huge amount of bandwidth and bit rates, the bandwidth will always be a limited resource. It is either limited because there isn't much of it in the atmosphere, or it's limited because of the integrated circuits that will have to have these signals passing through. There's always a bottleneck somewhere. And any type of signal, I think, even if it looks unusual, that can save bandwidth is a useful thing to look at, is a useful signal to look at. We have used this with something similar to the LTE carrier aggregated systems using LTE frames. So this spectral efficient signal is sitting within an LTE frame tested over an LTE channel. And again, we can see, if you look at the red versus the green, the red is one of these signals where we carrier aggregate 7 frequency bins compared to the LTE standard signal with 5 carriers aggregated. In other words, in the red, we have got 40% more data within the same bandwidth. And that results in a loss of 2 or 3 dBs. We can do the same looking at the backhaul of networks. So we did this at much higher bit rates, at 24 gigabit per second, using an optical transmission link. over an 80 kilometers of single mode fiber. Again, similar results were obtained. This is optical signal to noise ratio versus bit error rate. Saving bandwidth can result in worse performance, but only tolerable by a couple of decibels. Alternatively, maintaining the same bandwidth, we can increase bitrate. So there is this compromise. Do you have fixed bandwidth and increase bitrate, or do you want to reduce bandwidth and maintain the same bitrate? In all cases, there is a benefit. The main disadvantage is complexity. Most recently, we have tested this in the millimeter wave regime. So this work was done collaborative between us and Chalmers, the University of Chalmers in Sweden, Herbert Zerath group, a wonderful group that works on making integrated circuits, again mentioned earlier by Harish, the integrated circuits that can do the radio at these very high frequencies. And this is in what's known as the E band between 82 to 86, I'm sorry, not 68, 82 to 86 gigahertz. We're transmitting 8 gigabits per second over bandwidth that is changed from 4 to 2.6 or 2.7 gigahertz. A quite good reduction in bandwidth, and we get, again, similar results. We have, in this case, 2 dB power penalty, but all this bandwidth saving. In this case, incidentally, because we save bandwidth, then the SCFDM performs better because it has lower bandwidth, so it has less noise, right? So the same bit rate, but we have an energy advantage. And we have done the same with a system where the signal is carried in the radio over fiber, and we've got the same advantage. So what else can we do with signals? What else can new radio techniques, how else can new radio techniques help in systems like 6G that are looking at much higher bit rates and much more complex signaling, so we can do we can deliver the higher information content. Harish mentioned earlier about AI designed or ML designed constellations and constellation mapping, probabilistic shaping, and many other similar techniques have been commonly used, commonly studied, and more increasingly used in optical systems, and they can be used in wireless systems. So again, we look at OFDM and SCFDM, the spectral efficient system, with probabilistic shaping, and where the shaping functions are designed using ML techniques. And the aim in this case is to minimize error rate. If you have an appropriate receiver that does not need to be too complex, you can recover quite a bad constellation received into these constellations for spectral efficient FDM, which are similar to the ones that for OFDM. So more or less similar error rates, but this bandwidth saving here is only 20%. Or if you have the same bandwidth, you can increase the bit error. You can increase the bit rate. This is also using ML designed constellations with this spectrally efficient. So it's a mixed AI designed signals that will design specific constellation with specific bandwidth saving characteristics. And within the same bandwidth, we can send either 300 megabits per second or 400 megabits per second with a power penalty of nearly 2.6 decibels. So a designer or a system designer will have to decide which one of these do you want. Do you want to save bandwidth or do you want to save energy? And of course, since the days of 3G and onwards, the look at modified constellations and looking at systems whereby we can change the coding and the modulation according to the channel has been common. And in this case, what we will add is an extra dimension, which is the dimension of the spectral efficiency. So to wrap up, these signals will work. They do work, And I think they will offer a possibility of new type of signals, new radio for future systems. Indeed, several people in industry and people who are involved in the standards activities have been looking at these. And you know this when you see lots of patents starting to appear in something you've worked on, you know that maybe there's interest in these industrially. So wrapping up, SCFDM, of course, the signal that we worked on is not the only signal of this type, but it has specific advantages. And in my view, it can satisfy a lot of the constraints that I mentioned at the beginning. It can send more information within limited bandwidth and without compromising the signal quality, but probably at the expense of slight addition of requirement of energy and slight addition in complexity. And I will finish by just one slide to say that this work is not my work, it's the work of over 20 people who worked with me in this area and in related areas of signal design over the past 20 years or so. If anyone is interested, have a look at this paper that I'm quoting here, looking at these particular signals, and indeed have a look at lots of activities that are happening in the design of new radio for what will become the 6G system. And apologies if I overran. Thank you very much for listening.
Thank you, Izzat. There are a couple of questions for you in the Q&A part, so we cannot take them due to the time here, but if you could go and see whether you can give answers to these questions in the Q&A.
I will do.
Thank you very much.
Thank you.
Then we have one more presentation to go, and the presentation will be given by Yi Ma, who received his PhD from University of Liverpool in 2004. He thereafter joined the Institute for Communication Systems in University of Surrey in 2004, where he's now academic staff member. He's leading the multi-user signal processing group, and he's also the chair of Air Interface Club at the ICS and the work area leader of the 5G Innovation Center at the University of Surrey. He has authored and co-authored over 150 papers in journals and conferences, and he holds 4 international patents. So, Yi, please give your presentation.
Thank you, Harish, for your introduction. Let me share the screen. Can you see my screen?
Looks good. Just put it in the presentation.
Okay. First of all, thank you very much for my colleagues who have already given very great insightful introduction about 6G and perhaps physical layer as well. So this would allow me to quickly focus on my work to a very narrow topic about MIMO. The MIMO research we are doing here at the University of Surrey, 5G Innovation Center and 6G Innovation Center. So for the MIMO in 6G, so we specifically call this is 4N wireless MIMO. So what it is, so I will introduce later, and I also see some questions was talking about the machine learning for modulation or for the constellation design or something like that. So perhaps I can also partially respond to this question, which is given to Izzat, but because I will present some cases for that as well. So this work, I would like to acknowledge our group members who are contributing to these lots of technical contributions to this work. So what is 4N wireless MIMO we defined? So basically it's very simple. So 4 words: non-stationary, non-linear, non-Gaussian, and non-ergodic. So basically we believe that these are driving the fundamental paradigm shift in fundamental research anyway. So as Gerhard and Harish already mentioned that we have particularly looking for very high spectrum efficiency, latency, and reliability. So basically, if we really need a very high spectrum efficiency, so we need perhaps just simply increase the number of surface antennas, as I show here, in the picture. So basically, this is the site view of our University of Surrey campus. This is our 5G IC. And if we deploy lots of antennas, surface antennas here, you will see, well, effectively from a very large aperture, for instance, it is 45 meters, and to serve a user. Then you will see that even for a single user, the end-to-end, the point-to-point, the channel model is no longer wide sense stationary. So we will have to use a new channel model. So we have to consider basically the channel is spatially non-stationary, and perhaps we have to consider the user, the operator actually at the near field, is a near field. So this is something new that we have to consider. And there's already lots of papers published in this area, but still lots of work to do. And the other thing is, if we have so many antennas, as in 5G, we already investigated the use of low complexity MIMO, how to reduce the complexity. For hardware complexity, then we have to consider the use of low resolution ADCs, or we use hybrid MIMO, like hybrid digital and analog MIMO, something like that. And particularly, I mean, I want to mention, yes, there's probably we have to, we really consider a lot about the low resolution MIMO, but we really need to pay more attention to the power amplifier as well, because for MIMO, the power amplifier will perhaps introduce the nonlinear, non-Gaussian interference due to the non-linearity of power amplifiers, which was very rarely considered, I mean, in the literature or in the technical community. So basically the interference now we're considering is always linear, stationary, something like that. But in the future MIMO technology, perhaps we will have to consider the nonlinear, non-stationary, partially connected interference. And also because of the use of these nonlinear electronic components like ADCs and like power amplifiers. So although we use the linearization technology for power amplifier, but still non-linearity is still there. So in that case, perhaps our noise will no longer be Gaussian. We will have to learn how to handle the non-Gaussian noise and the interference. Well, when come to this low latency requirement for 5G or for 6G, we have to optimize for short length coded burst, something like that, or the short length transmissions. So in that case, Shannon's theory, Shannon's AEP principles no longer hold. So we have to have a really fundamental rethinking, how to design a code book, the communication systems, optimize it for non-ergodic communication or non-ergodic information source, something like this. All of them are very challenging. So these 4N means non-stationary, non-linear, non-Gaussian, non-ergodic. These are the new things that we have to look at in our fundamental research in the physical layer. So specifically for the massive MIMO, I would say, as I already said, the conventional wide sense stationary channel model can no longer be used for link level simulations, okay? Because it didn't reflect the non-stationarity, and we don't know if non-stationarity is there. So what will be the channel capacity behavior? What this fundamentally changes the channel capacity behavior in our link level study. So in order to facilitate our research in the link level or multi-link level, so we basically need a simple and mathematically tractable channel model. Indeed, there are a couple of very simple channel models exist. And for instance, non-identical, they distributed Rayleigh or rising, but I will later on show you some simulation results. So they cannot really reflect the true physical characteristics of these non-stationary channels. Well, so right, let me move to our work. So basically, we have recently developed a very simple and mathematically tractable non-stationary channel model for the ELAA, the extra large aperture array massive MIMO, as I have already shown here. But this model, we soon realized that it is also suitable for other like other distribution MIMO techniques or something like that. So it is not only limited to ELAA massive MIMO. So we use the MATLAB site view to emulate this kind of non-stationary channel where we deploy a very large aperture massive MIMO array here to serve users when users can really pop up somewhere in this area. And then we use the link level channel model to do the Monte Carlo simulations and to try to model in this kind of scenario with changing some parameters and then realize it. So what will happen? So as you can see in this figure, so the red color means this is line of sight area, and the blues and these are non-line of sight areas. So basically you can see, for instance, this user, well, located here. So in the middle, this bunch of lines, anyway, they are line of sight, and these are non-line of sight. This is corresponding to our randomly generated link level channels, like this way. And when we add in the shadowing effects under the fading effects, so basically you will see this is the generated fading channels corresponding to this model. So when users are located at different locations, it was the line of sight and line of sight, but then non-line of sight states are changing spatially, and accordingly their fading behaviors are changing as well. So here is the algorithm that we want to show. You see the algorithm to implement this kind of non-stationary channel is very simple. It's very, very simple, and just a couple of lines. So basically, it's very easy to support our link level or multi-link level Monte Carlo trials. And when we use this channel model to study this channel capacity behavior, so we show the CDF of the channel capacity using different non-stationary channel models or use a special case, which is IID Rayleigh. So if we use IID Rayleigh or conventional, the conventional non-stationary channel models that exist in the literature, you will see that because we use a large number of service antennas, you will see channel hardening effects is really there. So basically the channel capacity, because we have many service antennas, so you will see the channel capacity is there. It's very concentrated on this. And the variance is almost very close to 0. So that's great for MIMO, but is this really the truth? I mean, for our practical implementation, actually it is not. So if you see these color lines, which we use our new link level channel models to generate to study channel capacity, you will see actually channel hardening effects is not really that good. Okay, not really that good. So basically, if you see that, but interesting thing is if you see the users, because this is multi-link level simulations. So basically, if users are very closely located, they're very closely located. For instance, there are within 1 meter square, there are 2 users. Each user have like 4 antennas or 8 antennas. So basically, this red curve reflects the channel capacity variations. When users get more far from each other, and you will see the channel hardening effects getting better. I wouldn't say this is channel hardening, but their capacity behavior get better. So these are all the new features that spatial channel non-stationarity can bring to us and give us new challenges, new problems when we do MIMO research. So this is, I want to say, perhaps we should consider new signal processing techniques to handle those non-stationarity and perhaps non-stationary interference as well, because users are not fully connected, they are partially connected, and the interference are also not fully, wouldn't interfere in a fully connected manner. They are not stationary anymore. Right. The second showcase we are doing here for this MIMO is we found that in 5G research, we did consider this low resolution MIMO, low resolution ADC. And in the 5G time, actually, we use some linear approximation models to model this nonlinear behavior of the ADCs. So basically, we use approximation. So otherwise, the MIMO detection complexity is going to be very high. So, but here, after our very careful study, we found that the current linear approximation models, actually, they sometimes too easily assume that the quantization noise is Gaussian, and it is perhaps most of the time, the quantization noise or quantization distortion is assumed to be independent from the input of the ADC. So we here use a very mathematical way. We use the second order, we use a Hermite polynomials to study the behaviors of the ADC, and we found that perhaps we can use second order polynomial expansion to explain why the quantization distortion is Gaussian. And our research found that it cannot be always assuming as Gaussian, and but we can, in some particular conditions, yes, we can assume the quantization distortion is Gaussian, and it is indeed uncorrelated with the input signal of the ADC. But for most of the case, it is not. So we managed to find out the conditions when the quantization distortion can be considered as independent Gaussian noise. And moreover, we found that the new model does discover something new behavior, physical behavior that we didn't notice before. And I wouldn't really go to the detail, but these kind of new behaviors leading us to a new linear minimum mean square error channel equalizer for these low resolution ADCs, which is shown here, equation 62 in our paper. So if we use our new LMMSE equalizer for this low resolution ADC, and here I show this 2-bit ADC case. So all the colored curves are our LMMSE channel equalizers, and the black ones are conventional ones. So we can see for 2-bit ADCs, basically, sorry, I'm running out of time. Particularly for 2-bit ADCs, our proposed approach significantly beat the conventional ones. And because the conventional ones is too approximate. But when go to the 3 bits, I mean, we basically offer almost a similar comparable performance, because 3 bit is perhaps the conventional approximation is already good enough. So this is the work that we recently, the model we recently proposed for nonlinear and non-Gaussian. So very last one is I would like to echo to Harish's work, what Harish mentioned for the deep learning or machine learning for physical design for modulations. This is our recent work. You can find it from HV Chain Wireless.com early access. So we were researching whether it is possible for us to design a kind of blind MIMO detection. Blind MIMO detection here as a receiver for uplink, while we allow the users to have a offline jointly designed codebook. This codebook is for short block length to enable UILC. And so if we do offline deep learning, well, the channel in our simulations is a multimodal channels. And so as to mitigate the overfitting problem, channel model overfitting problem. So then through this end-to-end deep learning, so we found that our hypothesis that the blind MIMO detection can work very well, get supported. So basically, there does exist random code books that can be jointly designed such that the MIMO detection and multi-user detection doesn't really need any channel information. And when we compare our proposed approach with the conventional MIMO technology, like if we use 8x8 correlated MIMO channel, LTE correlated MIMO channel, so where we compare with our approach with the coherent MIMO detection, where we use the LMMSE channel estimator to estimate the channel, this is the performance we can get. And when we use this very well trained neural network, end-to-end trained, and at the receiver side, I would like to highlight that there's no channel state information. We don't do any channel estimation. Then you will see there's a huge performance gap between the coherent and this. I perhaps shouldn't say this is non-coherent, but at least for the online communication state, there's no need for channel estimation, equalization, such kind of things. But the joint codebook design does give us huge gain, and thus shows robustness to the channel uncertainty in the MIMO detection. And this is perhaps partially I can explain the power of machine learning for the codebook design. For the using blind MIMO detection as an example. So this concludes my my work and my presentation. And these are the reference papers I mentioned that you can perhaps, if you get interested, you can download them and have a read. Thank you very much. And yeah, that's it from my side.
Okay, thank you, Yi. I believe we had some plans to take some questions in the end, but however, we are already beyond our timeline. So I would like to thank all the speakers. Thank you for Harish. Thank you, Izzat. Thank you, Yi. And also thank you for our absent presenter. And once again, I would like to thank also the conference organizers, audience. I counted at the best time we had something like 240, almost 240 people listening to us. So that's a very good audience. And obviously, thank you for the speakers. And one more thing that 6G World has asked me to do is to thank our sponsor, who is the Virginia Diode. And therefore, thank for them. And I believe we are at the end, and we conclude the session. And see you in the next meeting. And goodbye.